Hello everyone and welcome back. Today's video is all about electric potential, specifically the potential at a point due to a single point charge and an electric dipole. These concepts are fundamental in understanding how charges interact with the electric field, and we'll break it down step by step to make it easy to understand. Let's get started. Let us now learn to calculate potential at a point due to a single charge. Consider a charge plus Q located at O, and we need to calculate the electric potential at a point P, a distance r away from the charge. OP is equal to r. Now, to calculate the electric potential at a point P, we use the relationship that work done per unit charge in moving a charge from infinity to the point P is equal to the potential at that point. Let's break down work done per unit charge in moving a charge from infinity to point P as sum of work done in moving unit charge from A to B, P to A, C to B, and so on till infinity. Let's begin by calculating the work done per unit charge in moving the charge Q0 from A to P first. The electric field EP at the point P due to charge Q is given by EP is equal to 1 by 4 pi epsilon naught Q by R square. Similarly, the electric field at point A can be written as 1 by 4 pi epsilon naught Q by RA square. If points P and A are very close, the average field EAP between these points can be taken as the geometric mean of EP and EA. Mathematically, we can write it as EAP is equal to square root of EA into EP, which is 1 by 4 pi epsilon naught Q by RA square into 1 by 4 pi epsilon naught Q by R square. So, taking the square root, we get 1 by 4 pi epsilon naught Q by RA into R. So, with this, we can calculate the magnitude of force experienced by a test charge Q0 over this region will be FAP, which is equal to Q0 times EAP, which is 1 by 4 pi epsilon naught Q0 by RA into R. So, therefore, the work done in moving the charge Q0 from A to the point P can be written as WAP is equal to work done is force into distance. So, force experienced is FAP into distance RAP. So, we know that this is the force. What is RAP? RAP is this distance, which is RA minus R. So, substituting this 1 by 4 pi epsilon naught Q naught by RA into R, and RAP is RA minus R. Simplifying, we get 1 by 4 pi epsilon naught Q naught. So, taking this as the denominator, we get 1 by R minus 1 by RA. Similarly, the work done in moving this charge from point B to A can be written as WBA. This would be RB minus RA. Similarly, for point BC would be RC minus RB. So, we can write it as the work done in moving this charge from point B to A will be WBA, which is 1 by 4 pi epsilon naught Q naught into 1 by RA minus 1 by RB. And from the work done in moving the test charge from C to B will be WCB, which is 1 by 4 pi epsilon naught Q naught 1 by RB minus 1 by RC. and so on. So the total work done in moving the charge from infinity to the point P would be sum of all these components, 1 by 4 pi epsilon naught q naught. So sum of all of the components would be 1 by r minus 1 by ra plus 1 by ra minus 1 by rb plus 1 by rb minus 1 by rc. This will so on, sorry, this will continue till 1 by infinity. So simplifying, we get the work done as 1 by 4 pi epsilon naught q naught. This component gets cancelled, this component gets cancelled, so on. So what will we will get with 1 by r and 1 by infinity into 1 by r minus 1 by infinity. We get the work, total work done is 1 by 4 pi epsilon naught q naught 1 by r minus 1 by infinity. Since 1 by infinity is 0, we get 1 by 4 pi epsilon naught q naught by r. Now, to calculate the electric potential at the point P, we use the relationship that the work done per unit charge in moving a charge from infinity to the point P is equal to the potential at that point. So, the potential at the point P, can be written as Vp, is work done per unit charge. So, which would be 1 by 4 pi epsilon naught q naught by r into 1 by q naught. Cancelling, we get the potential at the point P is equal to 1 by 4 pi epsilon naught q by r. So, the electric potential at a point due to the point charge is directly proportional to charge q and inversely proportional to the distance r from the charge, and it is positive or negative depending on whether the charge q is positive or negative. Now, what if there are multiple charges? The electric potential at a point due to a system of charges is the scalar sum of potentials due to individual charge. For example, consider the system of charges. Charges q1, q2, q3, q4, q5 at a distance r1, r2, r3, r4 and r5 respectively from the point P. The total potential V at point P is the scalar sum of the potential at charge q1, potential at point P due to charge q2, potential at P due to charge q3, due to charge q4, due to charge q5, so on. 1 by 4 pi epsilon naught q1 by r1 square plus 1 by 4 pi epsilon naught q2 by r2 square, 1 by 4 pi epsilon naught q3 by r3 square, so on. This can be written as summation I equal to 1 to here it may be pi. Suppose if there are infinite charges, we can get it as infinity by 4 pi epsilon naught q I by ri. This is the general equation. Remember, electric potential is a scalar quantity, so we just add up the contributions from each charge. Now, let's look at the potential at a point due to an electric dipole. An electric dipole consists of two charges minus q and plus q separated by distance 2l. Here we have considered charge minus q at point A and q at point B with the center at O. Let's say we want to calculate the potential at point P whose polar coordinates are r and theta. Note here OP is r and the angle BOP is theta. Here AP is equal to r1 and BP is equal to r2. This is the point P. Now the potential at point P due to the charge minus q at point A. is given by V1, and similarly the potential at point P due to charge plus Q at B is given by V2. So V1 is equal to 1 by 4 pi epsilon naught minus Q by R1, and V2 is 1 by 4 pi epsilon naught Q by R2. So the total potential at point P is given by Vp is equal to the sum of these two potentials. So V1 implies V2, which is equal to 1 by 4 pi epsilon naught minus Q by R1 plus 1 by 4 pi epsilon naught Q by R1. Sorry, Q by R2. This can be written as 1 by 4 pi epsilon naught, sorry, Q by 4 pi epsilon naught 1 by R2 minus 1 by R1. I have rearranged it. Let's simplify this equation further. Let us draw the normals from point A to the line joining O and P, from point A and similarly from point B. So these are the normals. From triangle BOD, we note that OD is equal to, this is L cos theta. Similarly, in triangle OAC, we can write OC is equal to L cos theta. For a small dipole where the distance between the charges 2L is much, or let me write it as AB is much smaller than the distance R from the point P, which is OP. Then with this condition, we take PB is equal to PD and PA is equal to PC. For a small dipole where AB is less than OP. We can approximate this distance R1 and R2 as R1 equal to R plus L cos theta and R2 equal to R minus L cos theta. Substituting this, we get this equation. V is equal to Q by 4 pi epsilon naught 1 by R minus L cos theta minus 1 by R plus L cos theta. Let's simplify this further. If we take this to numerator, this becomes epsilon naught R plus L cos theta minus R minus L cos theta divided, this is A minus B into A plus B, which is R square minus L cos theta square. So we can further write this as R gets cancelled, 2L cos theta by R square minus L square cos square theta. But we have considered 2L to be less than R for small dipole. So we can ignore this component. Therefore, we will become we can express the result Q into 2L as dipole moment T. So P cos theta by 4 pi epsilon naught R square. This result shows that Unlike the potential due to a point charge, the potential due to dipole is inversely proportional to the square of the distance. Let us now consider a few special cases for the potential due to an electric dipole. First case, when the point P lies on the axial line of the dipole, that is on the side of the positive charge. Here the theta is 0 and cos 0 is 1. So the potential at point P becomes P by 4 pi epsilon naught r square. Second case, when the point P lies on the axial line but on the side of negative charge, then theta is 180 and cos 180 is minus 1. So the potential at point P becomes minus P by 4 pi epsilon naught r square. Third case is when the point P lies on the equatorial line of the dipole, that is perpendicular bisector. Here the theta is 90 and cos 90 is 0. So the potential at the point P will become 0. Let's dive deeper into this third case where the point P lies on the equatorial line. As we saw, here the potential is 0. This is an important observation because it tells us that electric potential due to a dipole is 0 at every point on the equatorial line. When a dipole is placed in three-dimensional space, the equatorial line lies in the plane of the paper, and all the points in this plane have the same potential, which is 0. This characteristic is crucial because such a plane is referred to as equipotential surface. An equipotential surface is a surface where the electric potential is constant everywhere on the surface. Here is an important concept. The electric field is always perpendicular to an electric potential. This means no work is done when a charge is moved from one point to another on the equipotential surface because the potential difference between those points is 0. To summarize, we learned how to calculate the electric potential at a point due to a point charge and electric potential at a point due to an electric dipole. For a point charge, the potential decreases with distance, while for a dipole, the potential behaves differently depending on the position relative to the dipole's axis. The electric potential is 0 at every point on the equatorial line of a dipole. This equatorial plane forms a equipotential surface, and the electric field lines are perpendicular to these surfaces. The fact that no work is required to move a charge along the equipotential surface is a key concept. If you enjoyed this video, don't forget to like, subscribe and hit the notification bell so you don't miss out on more lessons. Let me know if you have any questions in the comments below. See you in the next video.